Fungi exist as transient spores in almost every natural environment, but their transition indoors into active colonizers requires one strict physiological trigger: elevated water activity on a viable organic substrate. Detecting this specific biological shift from a dormant organism to an amplifying threat requires exact scientific discipline. A casual visual inspection or an isolated air test is not a diagnosis. Deploying a generic testing methodology without evaluating the structural context guarantees compromised data. It blinds the investigator to hidden reservoirs, resulting in false negatives. To accurately map the microbial ecology of a compromised building, investigators rely on the Envirogyn tactical matrix. This operational standard demands that investigators constantly evaluate site variables, like humidity, material porosity, and HVAC airflow, to deploy three distinct pillars of diagnostics: surface, air, and chemical sampling protocols. Relying on any single method leaves critical blind spots. Only an integrated application of this matrix secures an accurate, defensible microbial profile. The first phase of this reconnaissance maps the physical contamination site through surface and bulk material sampling. The physical condition and location of the suspected growth dictate the specific tool deployed by the investigator. For dry, easily accessible surfaces, tape lifts are the primary extraction tool. Because the adhesive pulls the fungi directly from the material without crushing it, tape lifts preserve intact morphological structures. This allows laboratory mycologists to perform highly precise, quantitative, direct microscopy. Conversely, sterile swabs are deployed exclusively for wet surfaces, highly irregular geometries, or severely difficult-to-reach areas where tape cannot establish a clean seal. The data yield here is restricted. Swabs provide qualitative confirmation of the exact fungal species, but the disruptive collection method means they cannot be used to quantify the concentration. When contamination reaches deeper into a substrate, bulk sampling is required. This is a destructive method, removing physical sections of drywall or carpet to provide definitive analysis of deep material penetration. We supplement this with vacuum and dust sampling. Dust acts as a historical repository, trapping settled spores over long periods to reveal a building's long-term air quality baseline. These surface methods verify the exact location and physical footprint of a colony. However, they cannot measure how many spores have aerosolized, leaving the actual inhalation risk to the occupants entirely unknown. To determine the actual inhalation risk and track the airborne spread of particulates, the assessment must shift to the air column. The first objective of an air assessment is non-viable Walpole particulate testing, executing through spore traps. A spore trap captures all airborne elements on a sticky matrix. It does not discriminate, making it highly effective for calculating the total volume of airborne spores in a given cubic meter. The limitation is biological clarity. Direct microscopic examination of a spore trap cannot definitively differentiate between living and dead organisms, and many closely related spores look identical. That requires the second objective: viable or culturable sampling, utilizing multi-hole impactors or centrifugal samplers. Instead of trapping debris on an adhesive, this mechanism captures spores and cultivates living colonies on an agar plate. By growing the fungi, laboratories can sequence and identify the exact biological species. Success here relies entirely on media selection. Different fungal taxa require highly specific agar formulations and nutrient densities to germinate in a laboratory setting. Both methodologies are required for a complete picture. Spore traps measure the total volume of the threat, while culturable sampling isolates its specific biological identity. All of this airborne data is mathematically useless without strict mechanical precision during collection. Industrial hygienists rely on professional-grade hardware, specifically sampling pumps equipped with electronic laminar flow sensors. Constant flow control is an absolute requirement. These pumps automatically adjust their motor speeds to compensate for fluctuations in battery voltage, ambient temperature, and site altitude. The hardware must be strictly calibrated to the active protocol. Spore traps demand a heavy intake of 15 liters per minute, whereas culturable impactors require a gentle, highly controlled flow between 1 and 3 liters per minute to avoid destroying living cells. The investigator must also calculate the environmental dust load to dictate the duration of the sample. Oversampling pulls in too much debris, overloading the media and rendering the collection unreadable. In clean office environments, a sample might run for 5 to 10 minutes. In an active renovation zone with visible dust emissions, that duration is drastically reduced to 1 minute or less. Mechanical precision establishes the baseline. Without accurate flow calibration and strict timing, the resulting data cannot be scientifically verified or legally defended. Even with perfect surface and air sampling, visual inspections routinely miss severe hidden reservoirs trapped inside wall cavities. To detect active mold behind physical barriers, we track Microbial Volatile Organic Compounds, or MVOCs. This is the invisible chemical off-gassing footprint generated by fungal metabolization. Advanced chemical reconnaissance uses solid-phase microextraction, coupled with gas chromatography mass spectrometry, to isolate these specific chemical biomarkers in the air. Detecting precise compounds like dimethyl disulfide or geosmin provides a distinct chemical signature. It allows investigators to detect hazardous, toxigenic molds like Aspergillus versicolor, even when 0 spores are present in the room's air supply. This chart shows the total mold volatile organic compound curve, which investigators use to benchmark the severity of hidden growth by measuring nanograms per liter against a sample distribution. Readings that fall into the minimal to moderate zones indicate baseline, typical indoor ecology. These are easily manageable conditions. But when readings strike the elevated or high severe zones, the chemical footprint definitively proves massive hidden biological amplification within the structure. Chemical reconnaissance arms investigators with the ability to map and identify a biological threat that is entirely invisible to the naked eye, long before it physically breaches the drywall. Zooming out to the macro view of an environmental assessment reveals one absolute rule: no single indoor sample ever exists in a vacuum. Every piece of indoor data, every spore count, species identification, and chemical signature must be cross-referenced against simultaneously collected outdoor control baselines. Comparing the indoor ecology directly against the local outdoor environment is the only mathematical way to definitively confirm that true bioamplification is occurring inside the structure. By deploying precise surface mechanics, strictly calibrating airborne particulate capture, and utilizing chemical profiling to hunt hidden reservoirs, investigators systematically eliminate the risk of false negatives. This rigorous, multi-tiered matrix ensures every diagnosis is backed by unassailable data. It is the Envirogyn standard for tactical environmental compliance and operational readiness.